Hey everyone, thanks for coming. I know there are lots of good sessions, and I really appreciate that you all decided to come for this one, and I hope it would worth your time. My name is Andrey, and I won't bore you with details of my biography, but one thing that I guess is partially important is that I have a podcast. It's called Code Podcast, and we talk about kind of generic underlying concepts in software engineering. We try to talk to several people about the same subject and kind of stitch and put together a large overview of whatever topic we are investigating. And so this podcast led me to talking to lots of interesting people that are behind very cool projects. And I thought that some of the lessons, they had like a common thread through them. They were all to some extent, or lots of them, were to some extent about API and API design in interesting systems. And what I got to understand is that API affects everything. It affects what we can and cannot do with the system, how does the system perform, and how easy it is to make a mistake when using the API. And because I was talking to people that are from projects that you all probably use, I thought it would be cool to bring those projects into this talk and talk about those projects. Because projects like Git and BitTorrent and others, I think it's important to understand how those systems work, because they are also systems and they also have APIs. And not only that, we can learn certain techniques that we can later apply to our projects. But also it can improve our thinking processes, because when we see mistakes that those people made, or when we see decisions that those people made, we can kind of trace them and learn from that. So there would be 4 stories if I have time. If not, there would be 3 stories. That are kind of separate and independent from each other, but they're all about API design. First one is called "The Pixel is Not a Pixel." This one is about poor abstractions and how they limit what we can and cannot do in an API. And I decided to take an example from UI development, or graphical user interfaces, and specifically browsers, because this is something I have been struggling for a very long time. So let's just say we have a geometric task. We have a container, a box, a rectangle, and we have an element, another rectangle. Those 2 rectangles have heights, h1 and h2. Now we want to put an element in the middle of the container. And we want to calculate this x, and x is the offset of the element relative to the container. All right, quick quiz. I know the donuts, the sugar should give you the powers to solve this one. Who thinks it's the first answer? Raise your hand. The second one? Couple of people. The third answer? Donuts! All right, don't worry. I'm sure you would be able to solve it if you had like a piece of paper in 3 minutes. It's actually the second answer. So this is what x is equal to. How do we do that, for example, in the browser, in CSS? In CSS, it looks something like that. And it's fine, even though we got Flexbox maybe like 7 years ago or 5 years ago. Before that, you couldn't even center an element within the container. But it's fine. We can learn that, right? That's fine. Also in iOS and Android, by the way, it's fairly easy. But let's just, crack it up a notch. And let's just say that our container also has a grid inside. And this grid, each row is of height h3. And now we have the exact same task. It's just we want to center the element, but also tie the top border of the element to the grid. And we want to calculate that x. Right, I'm not counting on donuts for this one. But if you had 5 minutes with a piece of paper, you would figure out that there is a formula that actually does just that. Now the question is, how do we do this in CSS? How do we do this in iOS, in Android? There is no way to do this in the browser without using JavaScript. And even if you do that, it would be very painful with all the resizes and all this stuff, dynamics. It's possible to do in iOS and Android, but not with the layout. You have to write the actual code, Java or Objective-C, whatever you're using. And it's not a task from the sky. In the design in design systems and in design studies, they have this concept of a vertical rhythm that does just that. That vertically aligns elements to a grid on the page, because that's how magazines are done and all that kind of stuff, because it looks nice. So it's not from thin air, but it's very hard to do for some reason. What about testing this kind of code? This is ridiculous. Like even if we were to implement something like that in JavaScript or whatever, Android, we would have to spin off a simulator, like an entire operating system or a browser, and then take screenshots or do some weird stuff like that in order to understand whether our code is correct or not. I mean, best case, you get from the API the exact numbers. Worst case, you do screenshots. So a pixel on the screen is not actually a pixel. It's an object in a document object model that goes through layout process and so on and so forth that is hidden from us, that we don't control. And it seems like our knowledge of geometry, and common sense doesn't help us in creating websites. Why did that happen? Well, the thing is that I tried to trace this decision, and it seems like creators of the browsers originally thought that they don't need styling at all. In fact, they thought that the browsers themselves will decide how to display documents, and World Wide Web was just about documents, Even though at this time we already had books industry, we had magazines industry with very custom and interesting stuff. How would you do that in CSS today? This is from a magazine from 1980s or early 1990s. It's crazy. So after some time, browsers reconsidered, and they'd say, yeah, it seems like we want some kind of styling because it seems like publishers want some styling. And then there was a bunch of proposals, and CSS cascading style sheets win. One of the most important arguments why they won was, you know what? We think that the style of a document couldn't be designed by either the author or the reader on their own. We actually think that their efforts should be combined in some sense. This was the use case that they were orienting themselves, like drawing mustache on top of a magazine or something. Like, they tried to over-invent themselves. They tried to come up with something that would be completely new and something that was never done before. All right, that was probably not the best solution. Let's see what happens when a group of people comes with a different set of assumptions. And they say, all right, actually, you know what? We want to give users control over everything that is happening on the screen, over the layout process, the paint process, whatever is drawn, we need to have an API for that. And we need to layer it properly. And once you do that, Flutter, people did this in Flutter, this new framework for writing mobile applications from Google. And one of the nicest things there is they give you this layered API. And so if we were to implement our use case in Flutter, we would have to implement this method, get position for a child, for our container. And this method takes two parameters, the size of the container, the size of the child, and returns the offset, the thing that we already calculated using geometry. And I won't bore you with code, but what's important is that the code that is here looks almost exactly like the formula that we kind of came up before. So we see that the right abstraction not only makes it possible, it also makes it easy. We know already how to use the abstraction because it is the right abstraction. And it does, in fact, work. And what's important, here we can add text, remove text, and we also change the size of the grid, and it all sticks at all points. And we didn't have to write a lot of code. It was just 5 lines of code. And what's important, because Flutter re-implemented everything by themselves, all the painting processes, layout processes, we can write unit tests for that stuff. You don't have to spin off a simulator or a browser. It's just something that you can unit test. So my point is, properly layered API gives us freedom to build for custom use cases. What browser creators did is they created this really nice box of APIs to solve our very common use cases. But then publishers started complaining to some extent, we want advanced stuff, we want graphics, and they added canvas. They basically drill a hole into something that already exists in the browser engine. It's not exposed. And then they Now they are trying to add Houdini, which is hooks to layout and paid APIs. They are adding file APIs in 2018, is it? It's pretty crazy. We get this kind of Swiss cheese of an API. But the funny thing is that browser already had all that. It's just they didn't expose it, or they didn't design the API in such a way that would allow users to access to all of those things. And even funnier, the graphics engine that Chrome uses, for example, is the exactly same graphics engine called Skia that Flutter uses. So it's underneath, it's very, very similar, and the only thing that's different is an API. So another demonstration of the same principle. On the vertical axis, we have level of abstraction. On the horizontal axis, we have time to implement a use case. And for a boring use case, it's pretty trivial. Whatever you can do in HTML and CSS out of the box is pretty fast to do, pretty fast and easy. But once you start doing interesting use cases, the limit of the level of abstraction that you can use, it caps you. You cannot go higher level. You cannot use higher level abstractions. You have to go, assembly. You have to go C. You have to go closer to the hardware. And it takes longer time to implement, but it's possible to implement in lower level APIs. So, more abstractions is not the solution to everything. All right, second story is about mistakes in using the API, and specifically in context of programming languages. So programming language designers are weird people. They have to balance this kind of two very important attributes of a language: the cognitive load that they put on the user or on the user of the language, and capabilities of the language. This is the graph. So the amount of shots in the foot is on vertical axis. The learning curve is on horizontal axis. So stuff like assembly and C is fairly easy to learn on paper, but once you start using it, it's very easy also to shoot yourself in the foot. Stuff like Haskell is pretty hard to learn, but once you kind of get through the initial grunge, it's pretty impossible to shoot yourself in the foot because the type system is handling you in silky gloves, and you are feeling pretty good. That graph also, by the way, shows us that C++ made some weird choices. The point is that good abstractions actually help API users avoid mistakes. One of the hardest problems in programming languages and computing is multi-threading, working with concurrency. This is a photo from Mozilla office, and this poster says, it hangs really, really high up and says you must be this tall to write multi-threaded code. Why is that? Let's take a look at what Java did, for example. Java provides us with basic concurrency primitives. Synchronized is a keyword that tells us that at any point in time, no two threads can access a method or a block of code. Object wait, notify, and notify all are used to pause a thread and then maybe try to wake up the thread at some point. That's all. I explained you all Java concurrency in less than 30 seconds. How cool is that? Well, the thing is that to actually understand concurrency, you have to read this book in Java, to understand concurrency in Java, which is almost half a kilo, which is a great book, it's a Bible. But I mean, even once you read the book, you still are prone to mistakes because all your knowledge cannot protect you from some silly mistake because it's just very, very, very hard. So correctness is impossible to enforce. Let's take a look at choices that Rust made, for example. They said that concurrency is the hardest problem that we are facing, that we want to solve. And for this, we'll introduce a completely new concept of a borrow checker. So in the language, there is a completely new thing that you have to learn from scratch that takes significant amount of time to understand and comprehend. But then the thread safety would be enforced by the compiler. So once you've learned the concept, whatever you write, if it compiles, it's thread safe. It's beautiful. And at the same time, if you do feel comfortable and courageous, you can go down closer to the hardware and write unsafe code that works with multi-threading and implements send and sync traits It's basically like interfaces or type classes if you're into Haskell. And you would have everything the type system gives you, but for your custom stuff. So my point is expressive APIs require more effort from users, but at the same time, if you choose what's important and build around it and make sure that people cannot make mistakes in what's important, maybe it's worthwhile. All right, the third story is about performance. So oftentimes, especially at work, we had discussions about whether we need to adopt a certain API or the other kind of an API. And one of the arguments always, or often would be, let's just choose an API, whatever, and then on the implementation level, we'll figure out the performance. We'll make it perform. Well, I would like to point out that API is often a performance bottleneck. Let's take a look at an example. Let's just say we are talking about protocols. And in this specific example, network protocols. Who here ever used BitTorrent? No one? I thought so. Let's just say we are using BitTorrent, and a hypothetical person is using BitTorrent. And we have something that we would like to share, right? What does BitTorrent do? How does the sharing work? Well, the thing is that when we create a .torrent file, not we, whoever, we split all the data into chunks with a variable, not variable, but constant chunk size that we need to set. Now we have all those chunks, we enumerate them. Then we hash every chunk. We calculate SHA-1 hash from every chunk. And then we concatenate those hashes and hash them, and we have the magnet URL or whatever. The most important part that allows us to validate the torrent once we download the files. And this is 457. This is done, by the way, to just for the sake of integrity. This is done so that whenever a person downloads files from a torrent, they know that those are actually the files that the original person shared, and not some malicious stuff. This is pretty brilliant. But some problems start when we, for example, want to download only a part of a torrent. Let's just say we want to only download this last file that is just 4 megabytes of size. But we still want to verify that file. And the thing that we need for verification is 457 hash. But now to calculate 457, we need all other hashes. And each hash in SHA-1 is 20 bytes. And so the thing is that for this small torrent, it might be fine. But as we see, for example, as the size of the thing, of the data grows, the number of chunks grows linearly. And so the metadata size also grows linearly. And so at some point, when you have to, for example, when you are downloading a file that maybe is 4 megabytes of size, but you need about 2 megabytes of metadata for this file, it just stops making sense. Why not just make chunk sizes bigger? Well, the problem with big chunk sizes is that they're very hard to distribute through the network. Because if you have unreliable connections and you need to download uninterruptedly 4 megabytes from a peer, and that's a no-no. And recommended size of a chunk is usually 2 megabytes. So we have this dilemma, right? Size of metadata or size of a chunk. And we are always constantly in this trade-off battle. So what some people did, they created a DET protocol. In fact, Matthias Boos was on the podcast and he talked about it. And it's pretty neat. It's basically a peer-to-peer version data sharing protocol. In other words, it's like a decentralized open source version of Dropbox. So you have a folder, you can share it with your peers without a centralized server. They just, they'll share this folder in between each other without Dropbox entity. And it started as a way to exchange scientific datasets that are in terabytes of size. And it is now growing as a protocol for the peer-to-peer web, if it ever comes, But what's cool is also you can update your data and still all the things would work. Whereas in BitTorrent, the data that you share is static. If you want to update the data, you need to update the torrent. But yeah, what they did with performance is following. Let's just say we have Bob and Alice, and they want to share data in between each other. It's also 3 files. Very similar, we split the files into chunks. We hash the chunks, very similar to BitTorrent one-to-one. But now what we do is we just build a so-called Merkle tree of hashes. Basically, we take a pair of hashes, we concatenate them, we hash them, and we get the next level of hashes in that way. And in that manner, we calculate this tree, and now we have two heads, let's just say, or two top hashes in the tree, 0.8 and 3.0. Now, if we concatenate those, we get a root hash. And this root hash is also used as a unique URL to find a debt in the peer-to-peer network. So now, all Bob needs to do is to send the root hash to Alice. And using this root hash, Alice can find the actual debt. She can list the files. And let's just say she decided to only download the file number 3. So she downloads the chunks 6, 7, and 8. Now she needs to verify that whatever she downloaded, according to this root hash, is actually the thing she wanted. So what happens is she only needs to request 2 extra hashes, this 2.1 and 1.2, in order to verify the whole thing. How does it work? Well, the thing is that we already have chunks 6, 7, and 8, so we can calculate those hashes ourselves. Now, because we have those hashes, we can calculate further down the tree, hashes one by one. And that's how, using just 2 hashes instead of the whole thing, we were able to download files and verify them. So basically, instead of something that scales with the proportion of big O of n, where n is number of chunks, we have big O of log n, which is pretty cool. Just by changing the API, we got a performance boost. So what I'm saying is that even in network protocols, think also about HTTP 1.0, 1.1, and 2.0. Just by changing the API, we get great benefits in performance. All right. We're actually pretty good on time. You can relax. All right. This one is about change, because I think the notion of time and change are actually one of the most complex notions in API design. And generally in software, it's pretty tough. That's why I drew this fancy pictures to explain what I mean. So imagine we are building a social network. It's called Tabs and Spaces. It's about civil engineering debates. It's like Twitter, but positive. And we have a REST API. Everyone has a REST API. Twitter has a REST API. We also have a REST API. And it says the following. So if you want to create a post, you send a post request to this URL. If you want to update a post, you send a put request. If you want to get the list of posts, you send a get request. Super simple. But now, let's just say we have 2 people. We have Bob, the ERP developer, and he's in a particularly good mood. It's maybe Saturday, and he decided to share positive emotions with the world, and he writes this very profound thought: all frameworks have trade-offs. He does that by sending a post request. The machine, the server, returns an ID of the post. And then we have Alice, the cypherpunk. She's like, wow, Bob, this is a really profound thought. I would better share it, with a comment. She does that by sending a post request and getting an ID back. But then, let's just say it's Monday, and Bob went to his work, and he tried to maybe explore the future and try AWS Lambda, but then he figured out that actually the firewall in his enterprise corporation doesn't allow him to try out AWS Lambda. So he comes back home, upset, and changes his initial comment. He says, serverless is a lie. He does that by sending a put request and getting an OK from the server. But now what happens is Alice shared something that she didn't actually intend to share. There is something wrong there. Где же печать? But why did that happen? Like, it seems like we followed all the blog posts, and they all say that we have resources and we have get requests and post requests and put requests. What happened? Well, the thing is that REST had actually very good ideas. It said that, in the original paper, Roy Fielding said that everything is a resource. That's so far so good. Resources have unique identifiers. That's great. Resources can change over time. Oh, wow. Well, the thing is that there is a star there. The thing is that actually that's blog posts who say that. Originally, Roy Thomas said in his paper that there are static resources and there are dynamic resources. There is one paragraph, honest paragraph in his paper, where he says that those are different things. But this paragraph just got lost somehow in translation. Let's look at alternative assumptions. So let's look at Git. And there were 2 great Git talks today. So I will try to go into a little bit into the background of what's happening in Git. And Git has great assumptions. They are saying that facts in the world don't change. Facts are immutable. The fact that I just said puppy would never change. But what changes is labels or something. Labels, they change over time. For example, a label could be the last sentence that I just pronounced. It changes every time I pronounce another sentence. But puppy will forever stay in our minds. Puppy. All right, how does Git do that? So in file system, we have files. In Git is actually an object database. It's kind of hidden from us. It's in this .git folder that we never look into because it's magic. But this is what's happening. This is what's happening in the background. Every state of every file is stored as a blob object in Git object database. It's basically the contents of your file copied into another file, into a blob. And once the contents is there, the ID of the blob is actually SHA-2, doesn't matter. It's some kind of hash of this content. And this is the ID of the blob. And now we also have objects called trees. And trees are basically blob listings. So we have folders that are file and folder listings. And we have trees in Git that list other trees and blobs. And they also have an ID. And this ID is the hash of the contents. So inside this file that is called tree, there would be a listing with links to blobs and other trees. And once we hash the content of this object, we get the hash of the tree. And now these are the commits that we actually work with. And commits, all they do is they have a message, of course, they have authors and so on and so forth, but they also have a link to the root tree object and to 1 or 2 previous commits. That's all it is. That's the whole database. And it's pretty cool because everything in this tree is, in the Git part of the tree is immutable. Because we can change files, we can rearrange folders or whatever, but once we add those objects to Git database, it will reconstruct all the blobs, all the trees, it will reconnect them. So if the content of the file doesn't change, the blob doesn't change. If the content of the file changes, there is a new blob that is created, and then the new tree is created because the underlying blob was created, and so on and so forth. So the changes automatically propagate. It's a very smart system. And now, labels. So we have those tree of commits. What are branches? How do branches come in? Well, branches are basically labels. They are references. So we take a label and we put it on commit number 1. And the label says it's a master branch. In the file system, actually, in the .git folder, references are just files with the name of the branch. And inside the file, all you have is an ID of the commit. That's all it is. So if you change the ID of the commit in this file, you will kind of move the label onto a different position. Also a pretty smart system. So if we were to implement our use case using Git database instead of, I don't know, MySQL or whatever, if we were to ever do that, even though, let's just say we have a file called post.json that contains the text of the post, even though the address of post.json will be the same, once the contents of post.json changes, we have different blobs with different IDs. And so the whole thing would be reconstructed. And if we reference the content by the content hash and not by the name of the file or whatever, we get something that works and that is immutable. So my point is that the concepts of time and change are very, very hard to get right. And there are different ways how we can get around them. And one of the most common ones is just try to separate facts, what actually happened and what was the state at a certain point, from labels. Or in other words, separate snapshots from references to those snapshots. You know, what's your user state right now in this moment is different from what was your user object 2 weeks ago or whatever. Just a summary, you know, API design is hard because API affects everything. It affects what we can do with API, how does it perform, how easy or hard it is to make a mistake. But we can learn good design from systems we already use because those are actually great and they're very smart, and you know, there is a lot of things we can learn. And to get you started, I would of course recommend you to check out Code Podcast, because this is where we actually talk about this stuff. That's it. Questions? Everything was super clear right now.
I have a question regarding what you said about. Oh, sorry. I have a question regarding what you said about APIs being bottlenecks for performance. The company that I work at has set GraphQL as a company standard. And everyone has to use GraphQL because it's convenient for the front-end team and blah, blah, blah.
Yeah.
But my worry is a little bit that with REST APIs or other types of APIs, you can have, on the back end, like the abstraction, you know exactly what to expect query-wise. And I kind of wonder what I don't fully understand how you can let the client have so much control over the contract that you can still build for it performatively. So
Yeah.
what's your stance on like GraphQL and stuff like that?
Yeah, that's an important question. I think the thing is that at some point with GraphQL, you can actually, but it's just my opinion, I think you can get the same performance as from a REST API, but only once all the things are set in place and you know that your clients are not changing their way of querying things every second day.
Like caching?
No, I mean, ultimately you can, when your query from GraphQL hits the backend, it's your choice how to execute it. You can execute it in the same way as you would do with the REST API by building one huge SQL query, getting all the data and transforming it. You know, nothing prevents that. The only thing that prevents that is, do you know which queries are the most frequent and can you optimize for that? So I don't think in this specific case API would be the bottleneck. But unless maybe there is some problem with the payloads from the client to the server, maybe that's probably the only thing that I have in mind that might prevent high performance. Because in GraphQL, you have to send the whole query to the client. And if this query is very large and you have very slow upstream data stream, then potentially, yes, this might result in a bottleneck. And everything else, I think, could be mitigated if you know exactly what are the most common use cases for your API. All right. Thank you so much.